using OpenStax Calculus Volume 2 textbook. We are in section 3.3 and we're going to discuss trigonometric substitution. So there are certain expressions that come up in integrals and we don't have a rule to deal with them so far. So we have to kind of be creative and innovative and change them around a little bit to match something that we can handle. Luckily, people before us have gone through and done this to make rules for us, but we're going to show how this rule kind of came about right here. This is anything of the form square root a squared minus x squared. First, let me remind you, you cannot take the square root of 9 and the square root of x squared separately because there's a minus in the middle. They are an expression, not individual pieces that you can take apart. So we don't have a rule for the integral of square root 9 minus x squared. So we're going to use what's called trigonometric substitution, and we're going to go deeper into it in just a little bit. But for right now, we're going to say x is 3 sine theta. Well, if we're changing x to theta, then we have to also change dx. So dx would be 3 cosine theta d theta. So we rewrite our problem as the integral of square root 9 minus 3 sine theta squared times 3 cosine theta d theta. Well, if I square my 3 sine theta, I have the integral of the square root of 9 minus 9 sine squared theta times 3 cosine theta d theta. And I know that some of you are following along just fine, and some of you are thinking, I never would have thought of this. Why would I? You don't have to. This is going to be a standard practice for this type of problem. So it's not going to be something that you have to come up with everything on your own. Here, they both have a 9, so I'm going to pull that out and have 1 minus sine squared theta, 3 cosine theta d theta. All right. If I take the square root, nope, not yet. This follows my Pythagorean identity and equals cosine squared theta. So we have integral square root 9 cosine squared theta times 3 cosine theta d theta. We're going to take our square root and have square root of 3 cosine theta times 3 cosine theta, integral of, which is the integral of 9 cosine squared theta d theta. Now, there's more. We're obviously not done. We haven't taken the integral, but this is the point of trig substitution, because now we could use some of the rules that we learned in our other techniques sections about using the power reducers and things like that for cosine. Something else that I do want to show you before we go much farther is there is a triangle that we commonly use for this when we're using the square root of a squared minus x squared. We use a right triangle to help us out. So in our substitution earlier, we used x equals 3 sine theta. Well, that would really be the a that you took here. So this would be a sine theta. So if I divide, I have x over a equals sine theta. Well, if we put our theta here, opposite is x, hypotenuse is a, and if we did our adjacent squared plus x squared equals a squared, then adjacent squared equals a squared minus x squared, and if I take the square root, the adjacent leg equals the square root of a squared minus x squared, which is what we were dealing with. So just a little reminder of kind of how you would use that to deal with our other trig functions. All right, let's look now at our strategies. So first, make sure the integral can't be evaluated easily in another way. So even though all of the ones I have shown here, all three, could be integrated another way using use substitution, we can also do them this way. But use substitution would be easier. So once I have something of this form with the square root of a squared minus x squared, you substitute your a sine theta and your a cosine theta d theta. Okay, simplify the expression, evaluate the integral using techniques from the section on trig integrals, and then use your reference triangle to rewrite the results in terms of x. So looking at the same problem we were just working on, we're going to run through it again. A quick reminder, here is your a squared, which means that a is 3. That's where we got the 3. So we're going to say x equals 3 sine theta and dx equals 3 cosine theta d theta. And we've already done a lot of this, so we're going to kind of jump down to where we were. So we're going to jump down to integral of 9 cosine squared theta d theta. Once we get here, cosine squared theta, we can use our power reducer for this and have the integral of, I'm going to keep my 9 out here, 1/2 theta, sorry, 1/2 plus 1/2 cosine 2 theta d theta. And when we integrate that, we have 1/2 theta plus 1/4 sine 2 theta plus c. Distribute your 9 in here. So 9/2 theta plus 9/4 sine 2 theta plus c. Problem is, we have here a function in terms of theta, but we started with a's and x's, and we need to end with x's. So we're going to have to do some more work. The first thing we're going to do is right here, we're going to use our double angle identity, and instead of sine 2 theta, it equals 2 sine theta cosine theta. So 9/2 theta plus 9/4, oh, nope, that's going to be 9/2 when I multiply by that 2. 9/2 sine theta cosine theta plus c. Now we need to go back to everything in terms of x. So right here, remember theta's here, so that means that we have x here and 3 here, and here we have the square root of 9 minus x squared. If we want theta by itself using this, we'll divide by 3 and take the inverse. So sine inverse of x over 3. That's what's going to go in place of just theta. So we have 9/2 times sine inverse of x over 3 plus 9/2 times sine theta is x over 3, cosine theta is the square root of 9 minus x squared over 3 plus c. If we simplify a little bit, 9/2 inverse sine of x over 3 plus 3, 3, and 9 can cancel, so we have x square root 9 minus x squared over 2 plus c.